In the previous session, we had an intro to associative memory or content addressable memory. And of course, you know why we make use of a content addressable memory, shortly referred as CAM. Whenever you wanted to perform searching in parallel, number one. And number two, instead of identifying a storage location by the address, we want to identify by its content. In that case, you can think of using content addressable memory or associative memory. Now let us see its block diagram as well as the corresponding internal cell architecture in the current session. This is the block diagram of associative memory. You could see the diagram. The first register is called the argument register, labeled as A, which will contain the content to be compared. Assume it is going to be n bits, n, small n. N indicates the number of bits to be compared. The second register is called the key register. The key register is also containing n bits. N bits. This is used for the purpose of masking. For example, whether you want to compare all the contents of argument register, whether you want to compare all the bits or you want to compare only select bits or portion of bits present in the argument register. So for the purpose of masking, we make use of the key register. Whenever the key register bits are 1, the corresponding bits in the argument register should be compared with the words stored in content addressable memory. Whenever the corresponding bits are zeros in key register, those bits may not be compared. So that's the purpose of key register. It is used for masking. And then we go for the associative memory array and then the corresponding logic. It has got m words, n bits per word. So argument register store n bits, key register store n bits. That's for the masking purpose. But to compare all the bits of argument register with each and every word present in CAM, or you can compare only a portion of the argument register. That is where we make use of the key register's presence. When all the bits of key registers are 1, we compare the entire n bit word with the n bits present in all the m words present in content addressable memory in parallel. If only 3 bits are ones in key register, only those 3 bits of the argument register are compared with the m words present in content addressable memory in parallel. Okay. Now let us come to the associative memory. You can see the bottom half of the diagram. It has got m words and n bits per word. Okay. It has got the input. So what is the purpose of input? It is for getting let me say, values to be stored, and then read signal and then write signal. Read signal is meant for reading the contents of content addressable memory, and write signal is meant for the writing purpose. Then whenever each and every word matches with the content of argument register, presuming all the bits have to be compared. That means if all the n bits of an argument register matches with the word 1 of your content addressable memory, then the corresponding match register will be set. Corresponding bit in the match register will be set to 1. Assume there are going to be m words. The match register will be a m word register. Each bit of match register is equivalent to the corresponding word in your associative memory. For example, first bit is representing word 1. Second bit of match register is representing word 2. Third bit representing word 3. Ith bit representing word I. And mth bit representing word m. So whenever more than 1 bit is set in the match register, then you can perform reading operation. Let us come to the reading part bit later. This is the basic idea behind the argument register. In a nutshell, the argument register stores the content to be compared. It is an n bit register. Key register is meant for masking, to decide whether to compare all the n bits or only a portion of the content by masking certain bits. Okay. Then when you come to associative memory, it has got m words and n bits per word. And we have got a match register. Match register is also equivalent to match register size is m bits, 1 bit for each word. And the size of your CAM is equivalent to m by n. There are m words and each and every word store n bits. And finally, you get the output. What is the output? The output is going to be 0 or 1 depending on the match register content. Okay. Then you can perform the operation of reading or writing depending on what you require. Whenever you go for a search operation, we have to read the contents. And whenever, before you go in for storing something, we have to perform the writing operation. First, the content addressable memory must be made ready by writing contents into it and then perform searching operation. Whenever the match is found, then the output must be sent to the CPU or to any other processing part by the reading signal. So this is what a nutshell about your block diagram of CAM or associative memory. Remember, keep in mind, Argument register is storing the content to be compared, which is n bit. Key register is used for masking, which is also n bits. And your array memory size is m by n. That is content addressable memory size is m by n. There are m words and n bits per word. And match register is also m bits, 1 bit per word. And you have got signals, input signal, read signal, and then write signal. Let us come to the next part of it. This is an example I want to illustrate. In this case, the argument register contains, assume it is going to be a 9-bit register. So there are 6 bits, 6 lower bits, and topmost bits are 101. And key register contains 111, and the lower 6 bits are zeros, which means that the lower 6 bits need not be compared. We have to compare only the top 3 bits present in your key register. Argument register must be compared with the top 3 bits present in all the words in memory, not sequentially, but in parallel. So remember, the 101 is the content of argument register. In word 1, it is 100, therefore there is no match. In word 2, it is 101, there is a match. We are not bothered about the lower 6 bits contents. It could be anything. In the argument register, it is 4 ones followed by 2 zeros. Whereas in the case of word 2, it is 5 zeros followed by 1. We are not bothered about the lower order 6 bits. We are bothered about the high order 3 bits. So whenever there is a match, the corresponding bit in the match register, in this case for word 2, it will be set to 1. Remember, word 1, word 2, word 3, word 4, etc. are compared simultaneously by using your processing, let me say match logic. So that's the reason why content addressable memory is costly, and moreover it is expensive. That's one of the reasons why it is not widely used. It finds its usage only when the comparison time has to be less, and wherever you have to facilitate parallel processing. So this is a basic idea. Remember, we are comparing only the topmost 3 bits, the high order 3 bits of argument register with the words present. For illustrative purpose, we consider only word 1 and word 2, and we are not bothered about the low order 6 bits because the corresponding contents present in the key register is 0. That means they are masked. We are not bothered about the low order 6 bits. We are only concerned about the high order 3 bits. And there is a match found that is found with respect to word 2 and not with respect to word 1. And let us go in for the diagram. As I mentioned here about this cell, A1, that is the first bit. AJ is your jth bit of the argument register. AN is the nth bit of your argument register. Therefore, that is applied to K1. K1 is your first bit of the key register. KJ is the jth bit of the key register, and KN is the nth bit of the key register. It goes to your C11, word 1, cell 1, that is first row, first column. Word number 1, column number 1. Word number 1, column number J, C1J. Word number 1, column number N, that is C1N. So whenever, let me say, key register bits are 1, we compare the corresponding bits in word 1. Whenever they are matching with one another, M1 will be set to 1. What is M1? M1 is the matching register bit 1 with respect to word 1. So M1 will be 1 or 0. When it will be 1, whenever the argument register contents matches perfectly with your word 1. Whenever there is no match, M1 will be 0. Similarly, you are doing for word I, CI1, that is ith row first column. That is ith row first column. That's your first cell CI1. CIJ, ith row jth column. CIN, ith row nth column. And whenever CI1, CIJ, etc. up to CIN matches with the corresponding bits of AI, AJ, and AN, AI to AJ, and then AJ to AN, depending on your key register contents, MI will be set to 1. So MI is 1 whenever there is a match. Whenever the word I matches with your argument register content. Whenever there is no match, MI will be set to 0. So either it is set or reset. Similarly, word M. So this is the associative memory of M word and N words per word in the, let me say, elaborative point of view. So bit 1, bit J, and then bit N. Then whenever you go in for content addressable memory, I told you, it's internal comparison logic as well as storing logic is a bit complex. And it requires extra hardware circuitry. That's why it's expensive. And we require a match logic because we have to perform matching not with only one word. Matching has to be done simultaneously with all the words. How it can be done? Probably you can think before that. You can think of using your associative memory for one cell. What is one cell here? For example, one cell means C11 or CIJ. CIJ is ith row jth column. This is one cell. You see the logic here. Of course, you have studied. Let me not spend so much of time in explaining the hardware part of it. You know RS flip-flop. R input is meant for resetting and S input is meant for setting. The input can be either 1 or 0. If it is 1, it goes to yes. If it is 0, then you make use of an inverter. It's a NOT gate, it becomes 1. We make use of two AND gates. We perform right signal. Whenever the right signal is 1, depending on whether the input is 1 or 0, either R becomes 1 or S becomes 1. When R is 1, the flip-flop is reset. That means it will be going to the 0 state. If it is S is 1, then flip-flop will be going to the 1 state. That means you make the flip-flop status as either 0 or 1, depending on whether R is 1 or S is 1. And then that goes to the output of your S, that is called as CFIJ. Flip-flop I comma J, that's a generic feature. It goes to the match logic. In the match logic, AJ and KJ are given. Whenever AJ is 1 and KJ is 1, it has to be correspondingly compared with FIJ. When KJ is 0, the corresponding bit of AJ need not be compared with FIJ. And that goes to the word we normally call them as MI. The ith bit of your match register. It can be either 1 or 0. This is for one cell. The same thing should be done for all the cells. And whenever we come across reading operation, you give your read signal, the output of yes, either it could be 1 or 0. Yes is 1 or yes is 0. When I mean yes, I'm talking about the output. Either the flip-flop output is 1 or 0, depending on R is 1 or yes is 1. So if it is 1, you get the output. If it is 0, you also get the output. And you supply the read signal, you get the output as either 0 or 1 whenever you go in for reading the content of your content addressable memory. So this is the block diagram for an individual cell. The same thing should be replicated or combined together for M words. And n bits per word. This is for one cell. If the word is going to contain n bits, the same logic should be extended in cascade for n bits. So this is the basic idea about the match logic. And this is going to be how you perform the operations. Let me not go in for this diagram. I can say about the match logic. Whenever you go in for the match logic, this is one way of doing it. Another way, you know pretty well, you know about the exclusive OR gate. This is a diagram we have to remember. But because of want of time, you let us not spend too much of time on the match logic. You know exclusive OR gate. Whenever the bits are 0, output is different. That is, whenever the bits are different, output is 1 in the case of an exclusive OR gate. Therefore, the one input is from argument register, another input is from your content addressable memory location, word 1. So A1, let me say word 11. That is, A1 is the first bit of your argument register. W11 is nothing but the first bit of the first word. So this is why you make use of an exclusive OR gate, and then you feed a NOT gate. What is a NOT gate? Whenever the bits are same, the output becomes 0. When you feed them to a NOT gate, it becomes 1. The same thing you extend for all the n bits of that word, and you finally feed them to an AND gate. If all the bits are perfectly matching, the output of AND gate becomes 1. Whenever the output of AND gate is going to be 1, then you can think of then you can think of there is a match between your argument register content and your word content. Therefore, you can have an exclusive NOR gate combined together. Assume there are going to be 4 bits: A1, W11, A2, W22. W12, A3, W13, A4, W14. What is 11, 12, 13, 14? First word, first bit, first word, second bit, first word, third bit, first word, fourth bit. You feed them into exclusive NOR gate, you get the output as 1 or 0. Whenever there is a match, so you get the output, then transform. Whenever the bits are different of an exclusive NOR gate, the output is going to be 0. So therefore, in that case, there is no match between either the corresponding bit in the argument register with the corresponding bit in the word register. Finally, feed them to an AND gate. If in the case of AND gate, if all the inputs are 1, the output is going to be 1, and that is going to a match register. This is one of the simplest logic, but let me not go in for this diagram for the timing purpose or for the time purpose. Then, whenever you go in for associative memory, you can perform both reading operation and writing operation. In general, let me go into this block diagram. Yeah, this particular diagram. Generally, we store M words. Only one word will match with the argument register content, assuming all the key register bits are 1s. And you don't require the match register to be set and then performing the reading operation. Assuming there is only one word that is going to match, the output can be directly sent for further processing. Either the output is 1 or output there is a match or there is no match. Whenever there is no match, the output can be sent as all bits as zeros. How many bits are there? N bits are there. The N bits can be zeros, indicating that there is no match. Otherwise, whenever there is going to be a match, you can send the output as the corresponding word in the argument register to whichever word it is going to match with the let me say associative memory. Assume the word M is going to match with the content of argument register. The word M can be directly sent to the output without performing the reading operation, assuming there is only one word that matches. Sometimes more than one word in the content addressable memory may match with the argument register content. In that case, the corresponding bit in match register will be set. For example, M1, MI, MM are set. That means that the first word, ith word, and the mth word in your content addressable memory matches with the argument register content. Then what you should do, you have to perform sequential reading. That's the purpose of match register. You go through the sequential register. Wherever the bits are 1, read the corresponding word in a sequential fashion. This is the purpose of reading. And then how to perform writing. Whenever you're going for writing into associative memory or content addressable memory, it can be, if all the words are going to be written, if all the contents are going to be written before the searching operation is going to commence, you can make use of your random access memory principle, RAM principle. What you can do, you can have the address, and then using the decoder, you can use the address and store the content into the address using the general phenomenon of identifying location by the address and then storing the content into it. Later, you need not identify them by the address, but you can identify by the content. What is the advantage? If you are not going to use the address decoder, what is the purpose of address decoder? We have seen in an example. What do you do? If there are going to be 2 bits, it can identify 4 storage locations. What are they? 00, 01, 10, 11. So they either 00 means it denotes memory address 0, 01 means it denotes 1, 10 means it is 2, and 11 means it is 3. He normally called as a 2 to 4 decoder or 1 to 4 decoder. You would have seen in your map memory organization or implementation of memory map using RAM and ROM. We have seen. You can recall probably in our session 2. Now what I'm trying to say, use the address decoder. Instead of using n address lines, you require only m address lines. For example, I have got 1024 locations. How many address lines are required? We require 10 address lines because 2 power 10 is equal to 1024. By using 10 lines, I'll be able to identify 1024 storage locations using decoder. We normally call them as the address decoder. A decoder is one which decodes the given content. If it decodes the address, it is called address decoder. If it decodes the instruction, it is called instruction decoder. In this example, we are decoding the address, therefore it is called the address decoder. How many address lines are required? We require only 10 address lines. On the other hand, if there is no address, then to identify each location, how many storage locations are there? 1024 storage locations. You have to make use of 1024 address lines to identify each storage location. And then you have to store the content. So therefore, you can minimize the number of address lines by using the address for storing purpose. This is the purpose of storing or for writing. When I mean storing, it means it is writing. So therefore, first what you do, use the address of each and every storage. With the help of an address decoder, store the content into content addressable memory. Once writing is finished or once writing is done, then you can perform the reading operation. As mentioned before, either one word may match. In that case, no need for a read signal. The output can be directly sent. If more than one word is going to match, then the corresponding bit in the match register will be set. Why? Because the match register will have m bits, 1 bit for each and every word. The corresponding bit in the match register has to be checked for further, and wherever they are ones, then the corresponding word in your content addressable memory matches with the argument register. Then perform reading the match register content sequentially. And the last part of your CAM is that whether the word can be active or inactive, because we store contents in content addressable memory. Sometimes the word may be active or sometimes the word may become inactive. Therefore, how to distinguish whether a word is active or inactive? You can make use of one more register. That register is called a tag register. Whenever the tag register is 1, whenever the tag register bit is 1, probably what I can do, I can take up the diagram here. I'm going to have one more register called a tag register. Like match register, I'm going to have tag register. The tag register will also have m bits. 1 bit for each and every word. Whenever the bit is 1, the word is active. Whenever the corresponding bit is 0, the word is inactive. Therefore, when you go for comparison, instead of comparing only argument register and key register with the word, you can also take into account your tag register. You have to compare only those words which are active, and those words which are inactive, they can be ignored or they can be avoided for comparison purpose. Therefore, use a tag register and the content of tag register. For example, word 1, word I and word M matches. The corresponding tag register contents are 101. What does it mean? The word 1 is active. Word I is 0 in the tag register, which means word I is inactive. And word M is 1, which means tag. In the tag register, word for mth word it is 1, which means that word m is active. Even though word 1, word I, and word m are matching with the argument register content, but we are concerned only, we are going to compare only with word 1 and then word m, ignoring word I, because word I is inactive. Therefore, when you go for comparison in a parallel manner, you can minimize time or you can save time by looking into the tag register content. Therefore, one more register can be added, and that can decide whether the word stored in CAM is active or inactive. Only active words must be compared for searching purpose, and inactive words should be ignored or avoided. So that's a basic idea about your CAM. And let us stop here. Hope you have got an idea about what is CAM. Let me quickly say, CAM is called content addressable memory. Whenever you wanted to identify a storage location by the content rather than by the address, we call it as CAM. And whenever you go for parallel processing or parallel searching, in that case, it finds very, very useful and very helpful. And it is complicated because it requires matching logic. In addition to storage, each and every cell should require a matching logic that makes your circuit highly complex in nature. And it is also quite expensive, but it finds application where you go in for huge searching process. In the next session, we'll talk about one more type of memory called cache memory.